So today we're going to work on lesson 23. Lesson 23, it's really kind of one of those wrap-up lessons again, and this one is definitely going to be kind of making sense of the word problems that we've done before, kind of a way to approach them and solve them. So with this one here, we have modeling with quadratic functions. So we would have done modeling with linear functions and exponential functions in the past. Now we're going to use these quadratic functions. So this whole first page is a lot of information to help you understand how to use these. So when it's talking about these, it's the mathematics of objects in motion. So that's the very first ones that we're going to do. So it says any object that's free falling or projected into the air without a power source is under the influence of gravity. So anything that is falling, anything that's moving, as long as there's not something pushing it forward or against gravity, it's always going to be influenced by gravity, and we'll see it. I mean, if you have a rocket or something, it still has gravity acting against it, but it's going to overcome it. It won't be as big of a deal. So all free-falling objects on Earth accelerate towards the center of Earth, or downwards for us, at a constant rate. So if we're working in feet, then we're going to use this negative 32 feet per second squared. Or if we're talking in meters, then we'll do negative 9.8 meters per second squared. So that's what we're going to use when we're working through this. So that would be our G. So anytime we'd see Earth's gravity, it's represented by G. So that'd be this point right here in the equation. So the acceleration rate is indicated in the physics formula. So this would be a physics formula here. And it's going to represent the relationship of the object and then how much time has passed. So it's going to talk about the height of the object. How high off the ground is it over a certain amount of time. Look at these here. We see that this number in front, when we're working with projectiles, or we see a baseball player threw the ball up in the air and it came back down, with all those equations, we end up seeing a negative 16 in the front because we're talking about feet. We're measuring it, the total height in feet. So we have this negative 16 because we take the negative 32 times a half, and it's just going to become negative 16 in the front. We've just combined those two together. So it says here you have half of it, so you're always going to have negative 16 or negative 4.9. Just depending on if you're working with feet or you're working with meters. So when you get to your homework, make sure you pay attention to that. Is it in feet or is it in meters? So the next part here, the rest of these, it takes a little bit of time. You just kind of got to understand the variables to work with it. So h is going to be the height. So when you see h of t, it's height at a certain amount of time. That's t. Time is represented, or t represents time. So it would be from the beginning. So once the baseball player let go of it, then we're counting the clock from then on. The next part is v. So this is velocity. So this is our feet per second or meters per second. So this v naught is going to be your velocity. And then s is going to represent displacement, how far it moved in feet. And these ones you're not going to see an s. I don't think on your homework you'll see an s, or any of these examples we'll see an s here either. So the other thing is we use subscripts. So with this one it's v0 or v naught. So this one is going to be our initial velocity. So anytime you see a v0, that's at time 0. So our initial velocity at the very beginning, and then also our initial height at the very beginning. Once we start this, what is the height that we start at? What is the initial speed that he throws the ball at? So then you can get this right here. This is going to be the equation that we work with. This one would be if we're using feet, and this one would be if we're using meters. So we're going to use those on these examples. So exercise 1. So Chris stands at the edge of a building at a height of 60 feet and throws a ball upward with a initial velocity of 68 feet per second. The ball eventually falls all the way to the ground. What is the maximum height reached by the ball, and after how many seconds will the ball reach its maximum height, and how long will it take to reach the ground? So there is a lot in that question, and these A, B, C, all these letters are going to help us kind of work through that. So what units are being used to solve this problem? Again, like I said in this one, you have to make sure, is it meters, are we using feet, are we using seconds? So you just kind of want to write those out. So when we're looking at this, we're going to use feet. So we're going to say height is in feet. Then it says, okay, what is our velocity? So our velocity here, velocity is feet per second. And the last thing here, what would our time be? Time is measured in seconds. So, next part, B, what information from the contextual description do we need to use in the function equation? So, the very first thing, you just kind of remember gravity, since we're working with feet, is going to be negative 32 feet per second. So, the next thing, we need to know his initial height, so his HO, height at 0, is going to be at 60 feet. His initial velocity, or V0, is going to be at 68 feet per second. And that should be all. So then we can write out the equation. We can write out this function. So this negative 32, if we remember from this, it's going to be times a half. So we're going to get negative 16. I'll just put h of t. That's going to equal negative 16 t squared. And then our initial velocity is our next one. So it's initial velocity times time. So plus, our initial velocity was 68, and that's 68t. And we also add our initial height. So that's the last part here. So our initial height is going to be at 60. So what is the maximum point reached by the ball? After how many seconds did it reach that height? Show your reasoning. So there's a couple ways we can go about this. We can factor this and figure out the intercepts, or we can complete the square. For this one, we're actually going to factor it. It'll be a little bit easier. So we can pull negative 4 out of all of those. So we'll have h of t, and that's going to equal, so we'll pull out a negative 4, and we'll be left with 4t squared. This one will become minus 17t, and then minus 15. Okay, now we can work on factoring this out. So we'll use the AC method. So 4 times 15 is going to be negative 60. So then we can look at factors of negative 60. So we also need this to be negative 17. If we do negative 20 times 3, that is actually going to be the combination that'll get us that. So if we do negative 20 plus 3, that'll get us negative 17. And multiply together, you get negative 60. So we'll rewrite this out. Remember, this right here just splits the middle term here. So it'll be 4t squared minus 20t, because we're splitting the middle term, plus 3t, and it's minus 15. So all that is equal to h of t. So then the next part is we can use the box to figure out the different factors. So we have 4t squared, and this one's, we'll put 3t here, negative 20t here, and then negative 15. So when we get this t squared, to get that, we have to have t times t. 4, we can split that up, 4 and 1, or 2 and 2. For this one, we're going to split it up 4 and 1. 3 is not going to be easily divided by 2 or 4, but negative 20 can be divided by both. So for this one, we'll go with the bigger number, so it'll be 4, and so this will just be 1t. So t times what will give us 3t? That's a positive 3. And then 4t times negative 5 will give us negative 20t. So negative 5 times 3 will give us negative 15. And so then we have our factors on the side. So h of t equals, that'll be negative 4. And then we'll take this side here, 4t plus 3. And we'll also have t minus 5. Okay, so then we can solve for what our intercepts would be. So if we solve for the intercepts, for this one we'd have 4t plus 3 equals 0, or t minus 5 equals 0. To solve this one, we'll subtract 3 from each side. So then we get 4t equals negative 3 divided by 4, and we get t equals negative 3 over 4. So then on this side here, we'll add 5 to each side. So we had t equals 5. Okay, we were almost done. So the next part here is we're going to have to figure out where the vertex is. Since we're trying to find the maximum height or maximum point that it reached, we need to find the vertex. So this is actually useful for the next question. So we'll go to D real quick. How long did it take the ball to land on the ground after being thrown? Show your work. So we just showed our work for this one. So if the ball is thrown at 0, it takes this 5 seconds to get there. This negative we aren't going to use because it's not possible to throw it backwards in time, but at 5 seconds is when it would reach the ground. So 5 seconds, and we just put work on C. Okay, so then we're still working at the max. So to figure out the vertex, since it's symmetrical, we can combine these two and find the average. So we have 5 minus 3/4 divided by 2. So that's going to equal 4.25 over 2. And that'll equal 2.125. So that is going to be our x value. So what time, after how many seconds did it take to reach the ground, or reach that height? So the vertex is going to be at 2.125 seconds. So it took 2.125 seconds to reach the top. And then we'll plug this into the equation and figure out what it would be. So if you plug it back into the equation, you're going to end up getting 132.25. So that's going to equal your height. So all I did was, this is our t at our vertex. So I took this, plugged it back in. If you plug it back in, you'll get 132.25, and so that would be our maximum point. So 132.25 feet, that would be the maximum point, and it's going to reach that point after 2.12 seconds. So then here would be kind of our work and our reasoning for that. So last part here, graph the function of h of the ball and phi of time, blah, 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 blah. So you can use those key features. We just found them so we found our vertex, we can use that. We also found our intercepts, but really you'll want to use your intercept, your vertex, and then you can also use your initial height of 60. So I want you to attempt that and then come back and I'll have a graph for you. Okay, so this would be the graph version of that equation. So again, I just graphed the initial height of 60 feet. It's going to go up until it reaches the maximum at 2.125 seconds, and it'll be at 32.25, and then it'll come back down and reach the ground at 5 seconds. So we just need those 3 points, and we can get a graph of this. Something to remember, again, this is not he threw it up in the air and it traveled 5 units out. This is all would be in a line and just go straight up and then come straight back down. But what we're measuring is we're measuring feet or height. That's going to be in feet. And we also measure time, and that's going to be in seconds. So that's going to be important to remember. We're not measuring how far away from the building he threw it. We're measuring his height versus time. So that's just something to keep in mind. So that would be the graph for E. Okay, on to the next one. So the next one is going to be this business application. I believe we went over this a little bit in the last lesson, but we're really going to go more in depth with it now. So quadratic functions can be used in a business application to figure out the optimal price at which to set something at. So which we can look at is a couple things to maximize our revenue, maximize our profits. So couple just kind of real quick variables for you to pay attention to. So we use C for cost, a lowercase c is going to be the cost, P is for price, and Q is for quantity. These are going to be individual variables, so like the cost of 1 unit, the price of 1 unit. So then the total production cost, we're going to use an uppercase C, sorry. And then for total revenue, an uppercase R, and total profit, an uppercase P. So I would underline those. Those are going to be important when you're working with these, just to kind of keep them straight. So a couple or a little bit of vocab here. So the unit price is going to be the price per unit. So if I'm selling pencils, I decide to sell them for $1 each. That would be the unit price. So the next one here is the quantity. So if I'm selling these pencils and I sell 50 pencils, that would be the quantity that I sell. So the revenue is going to be the total income based on the sales. So going back to the pencil example, I take this pencil, I sell it for $1, and I sell 50 of them. Total amount of money or revenue that I get is going to be $50. So the next part is unit cost or production cost. How much did it cost you to make it? So let's just say, again, say this thing cost me 50 cents to make. I sell it for $1. So the unit cost would be 50 cents per pencil. In the profit, we're going to take how much it costs to make, or how much revenue you have minus the total cost to make it. So when we're working with this here, again, let's say this pencil, I took my pencil and I said, okay, sold 50 units at $1 each, that's going to be $50, but I had to pay 50 cents to make each one. That's going to be $25 total that I had to spend to make them. I made $25 selling these. So that would be one way to kind of look at this. So there are also a couple other formulas that we can use, and you're going to see these coming up. So total production cost is going to be the cost per unit times the quantity of the items sold. So how much did each cost, and then how many did we make? Total revenue, how much did they sell for, how many were sold, and then you take your total revenue minus your production costs, and you get your profit. So this next part here is going to kind of work through these. When we're working through these, normally they're going to be linear equations, but we're going to take them and change them into quadratic so that we can see the optimal points by working with them. So this one right here, it says a theater decides to sell special event tickets at $10 per ticket to benefit a local charity. The theater can seat up to 1,000 people, and the manager expects to sell all 1,000. To maximize the revenue for this event, a research company volunteered to do a survey to find out whether the price of the ticket could be increased without losing revenue. The results show that for each dollar you increase it by, you sell 20 fewer tickets. So we're going to end up creating a couple equations that will multiply together in order to solve this. So we're going to let X represent the number of $1 price per ticket increases. So our base price is going to be $10. If we increase it X amount of times, we're always increasing it by $1 each time. So it's going to be plus 1x. So this would be our way of representing this. So then for the next one, use the survey results to write an expression representing the possible number of expressions resulting to write an expression representing the possible number of tickets sold. So originally we would sell 1,000. If every time we increase it, we are losing 20 people who would be buying tickets. So we take this 1,000 minus 20 times however many times we increase the price $1. So for C on the next one, it says using X as the number of $1 ticket prices and the expression representing price per ticket, write the function R to represent the total revenue. So when we're working with this, we can multiply these two together. So we have R, our revenue, that's going to equal, so we have this 10 plus 1x, 10 plus 1x, and then we can multiply that times 1,000 minus 20x. So all we're doing is we're using this equation right here. Total revenue, price per unit times the quantity of items sold. This is our price per unit down here. This is how many would be sold. So we're going to multiply those two together. For this one, you can leave it in factored form. That's completely fine because then you can end up finding the maximum using that. The other option is to multiply it through. So we'll multiply it through just to see what that's like, so we can work with that. So for this one, we get 10 times 1,000, so we get 10,000. Remember, you get the FOIL. And then we do 10 times negative 20x, so it's going to be minus 200x. And then x times 1,000, so plus 1,000x. And then x times negative 20x, negative 20x squared. So I would rearrange that so that you have your x squared in the front, followed by the x, followed by no variable. So when we rearrange that, you're going to get negative 20x squared. Combine these two, so you'll get plus 800x and then plus 1,000, or 10,000. So R equals. Okay, so how many $1 ticket price increases will produce the maximum revenue? So when we're looking at this, we can approach this in two different ways. We can either use this standard form, complete the square, and then we'll find our vertex form in which we'll have the maximum amount, or we can use this to figure out our different our intercepts, use that to figure out the maximum value, or the midpoint. So personally, I prefer kind of doing this way. I think it's a little quicker. Completing the square, we've had some practice with that, so I'm hoping you can do that without me having to show you on this one. The next time I will show you. So if we're going to do this with the factored form, so we have 10 plus x, that's going to equal 0, or we can have 1,000 minus 20x and set that equal to 0. So for this one, we subtract 10 to the other side, x equals negative 10, or this one, we're going to subtract 1,000 to the other side, so negative 20x equals negative 1,000, divided by negative 20. So when you do that, you're going to get x equals 50. So x equals negative 10 or negative 50. So then with this, we're going to have to find the midpoint where our vertex would be. So negative 10 plus 50 divided by 2. That's going to equal, so this is on top will be 40, divided by 2 is going to equal 20. So at 20 increases, $21 increases, we are going to hit our maximum value. So when we're looking at this, so we found out how many increases we have to have. What is the price of the ticket that will provide the maximum revenue? So we can take this 20 and plug it in for x. So we're going to take 10 plus 20. So our total ticket cost will be $30. So then what is the maximum revenue? Then we can really fill this in and work it. So we already kind of worked out this front part here. So we'll have R equals $30. That's going to be times 1,000 minus 20 times 20. So you have to remember to use this x value. So when we work this out, you're going to get 30 times this in here was going to be 1,000 minus 400. So we get 600. And that's going to end up equaling $18,000. So this is how much the maximum revenue would be. So the next part, how many tickets will the theater sell to reach the maximum value? So we're looking here, they need to sell 600 tickets to reach this maximum value. Just kind of looking at here, you take 1,000 minus your 20 times 20, and that'll give you 600 that you need to sell. So it'd be 600 tickets. How much more will the theater make for the charity by using the results of the survey to price the tickets? So how much more will they make by increasing the price as opposed to if they left it? So we know that they made $18,000 by changing it. If they had left it, they would have had $10 times 1,000, and it would have equaled $10,000. So if we take 18,000 minus 10,000, they increased it by $8,000. So by using this, they ended up gaining $8,000. So these are a couple really good examples for you. On these next ones, I want you to work through them, give them a shot, see how you can do. Don't spend any more than 10 minutes on either one of them. Take 5 to 10 minutes, practice it on your own, wherever you're at after somewhere in that range. If you are just hopelessly lost, then take a break and just kind of watch, and I'll explain them, going through them. So exercise 1 and then exercise 2, I want you to try and work through. again, you probably will not finish them. They are pretty lengthy, so just take your time, give them a shot, see what you can do, and then when you're done, come back and I'll help you with them. So for these ones here, for exercise 1 and 2, I've actually worked them all out. You're just going to have to listen and I'll walk you through what I ended up doing. So this first part here, it says 2 rock climbers are going to try an experiment while scaling a steep rock face. They each carry rocks of similar size and shape. So one's going to climb 400 feet, the other one's only going to climb 300 feet. So the first one's going to drop their rock, and a second later, the other climber's going to drop their rock. And they're just going to see how long it takes for them to fall. So we're going to assume we're only looking at the vertical position, so we don't care about the horizontal, how far apart they were. And the other thing, I like how it says no climbers injured in this experiment. That's good. But the other thing is, yep, that just escaped my memory. So only worry about vertical position, and we really need to determine what variables are going to be what. So for here, we're going to have height 1. So this is going to be the height of the rock after it's dropped by the higher climber. And then H2, that's going to represent the height of the rock dropped by the lower climber. T will be the number of seconds after the top climber, the one at 400 feet, after they drop the ball. And then the other one, T minus 1, is going to be the time after the lower climber has dropped the rock. So we can end up creating 2 different equations here. So we're using this original equation that we have at the very beginning. So we have this negative 16t squared. We're working with feet, so we know that we're working with that. The next part is our initial velocity. If they're just dropping it, there's going to be no initial velocity. They're not throwing it down, they're not throwing it up. So our initial velocity will be 0, so that whole line is just removed. So this whole term is just gone. It's 0 times t, we don't care about it. So then the next one is the initial height. This is where we're going to get different numbers to put in. So for the first one, we have negative 16t squared plus 400. 400 is their initial height before dropping it. And for the other one, we have negative 16, but now we said our time for this one is going to be t minus 1. So we're going to do t minus 1 in parentheses, square that. That's our time. If we had a middle term, we would replace that one with t minus 1 as well. But we don't, so we can just not worry about that one. And it's going to be plus 300 for this. So all that's because we don't have an initial velocity. That's why we aren't going to have that t minus 1 in the middle term. So here would be our equations that we're working with. So then the next part is going to be B. So it says assume that the rock falls to the ground without hitting anything on the way. So that was the other part I was going to say. When they're dropping these rocks, we're just going to let them drop, and we're going to assume that they aren't going to hit anything as they're falling. So it says which one of the 2 rocks will reach the ground last. So show your work and explain how you know your answer is correct. So by working through these, so I did height 1 over here and height 2 over here. For the first one, the way I would solve these is we can just subtract the 400 over, divide by each side, and then square root each side. Just kind of that completing the square, the way we solve those. I'd use that mentality for this one, but you just skip the step of completing the square. It's kind of unnecessary to determine which one hit the ground first. All we're doing is seeing when our height is equal to 0. So that's why I said each one of these equal to 0. So for this one over here, I subtracted 400 from each side, then I divided by negative 16 to each side, and then I square rooted each side. When I square root each side, I have t is going to equal a positive and a negative 5. The only one that really matters to us is the positive 5. The negative 5 isn't going to have any bearing. He didn't throw the rock backwards in time. He can only go forwards in time. So it took it 5 seconds to reach the ground. So then the height of the second climber we're going to look at now, and we can do the same thing. So we'll subtract 300 to the other side, and then we'll divide each side by negative 16. When we divide the negative by negative, those are going to cancel, but I wouldn't write this as a decimal. It's going to be complicated once we square root. If you wanted to, that's completely fine. So then we'll square root each side, and we'll get t minus 1 on its own, and then we'll get plus or minus the square root of 300 over 4 plus 1 when we add 1 to each side. When we're doing this, the square root, the 300 is not going to break down easily, but the 16 will. That's just going to become a 4. That's how I got the 4 here on the bottom. You have to pay attention to the plus or minus too. Make sure you put that on the front. So then to get t on its own, I added 1 to each side, and then this would be the form that before we get the actual numbers. When you're using that, for this one, it's saying which one reaches first. Unless you're really good and you can tell what these are right off the top of your head, I would use a calculator, plug them in, figure out just about where they would be, and then we can see the difference between the two. So the answers here are approximately negative 3.3 and 5.3. So again, we only look at the positive value here. We're not going to look at the negative because he's not throwing it backwards in time. So we have 5.3 seconds and 5 seconds. So which one took longer? It's actually the person who dropped it 100 feet closer to the ground. By waiting it that extra second, it ends up making it that much longer. So the next part here, C, it says graph the two function, identify key features, and so on. So I'm going to explain how the graphs will show which one hits the ground first. So when you're working with this, I scaled it by 20 going up. That way I can get 400 at the top and 300 in there as well. The 400, that's the initial height at 0. So at 0 time, he drops it from 400, and it's going to start going down until at 5 seconds, it's at 0. The other one, it doesn't start until 1 second in. He's holding it, and then after a second, he drops it. And that one goes till 5.3. So I ended up graphing just using those 2 points and getting a general curve. To be more precise, I should have plugged in 2, 3, 4, or at least one of them and seen what numbers I would have gotten in the equations, and then I can use that to estimate a better curve to this graph. So that's what I would do in the future with a little more time. Okay, and the final one, D, does the graph show how far apart the rocks were when they landed? No, it doesn't. When we're looking at this, it's only showing us the vertical height compared to time. It doesn't say anything about the horizontal time or the horizontal distance that it travels away. So that's just something you have to keep in mind. Yes, this graph looks like it's traveling horizontally, but all we're doing is measuring the height at a given time. So at 2 seconds, it should be about this height. 3 seconds, about this height. And so that's all we're looking at. It has nothing to do with the horizontal. Okay, so for exercise 2, it says Amazing Photography Studios took school pictures and charges $20 for each class picture. The company sells an average of 12 class pictures in each classroom. They would like to have a special sale that will help them sell more and then increase their revenue. So they hire business analysts, and they determine that if you reduce the cost by $2 each time, you're going to sell 5 more pictures. So we're going to write a function to represent this. So we really need to determine what our variables are going to represent. Our x is going to be the number of $2 reductions. So every time we decrease it $2, then we would change the x by 1. So the price per reduction is going to be 20. So this original $20 minus 2 times that reduction price. Or 2 times the number of reductions. So if we reduce it 10 times, then they make 0 money per picture. So the quantity per classroom, they would originally start with 12, and then every time we reduce it, we'll get 5 more. So this would be our expressions. Our total revenue is going to be the cost, or the total profit, I'm sorry. So the cost to buy it for the consumer times the quantity. So for this one, we can leave it like this. I'm okay with you just writing it out like that, and that is your equation, or you can get it smaller, or simplify it into something like this, where it's in standard form. So it says, what should the sale price be? So when we're doing this, we're solving for the maximum. We're looking for that vertex, where it would be when it hits the maximum, and that's how much money they can make, and this is what they should change their price to. So what I did here was I took both of these and I did the other way, where we would find the x-intercepts and then use them to find out what my y is going to be, or what my x is going to be by taking the average of them. So I use that version. You could use completing the square. It's not the easiest completing the square to work with, but you could definitely do that as well. So to figure out what my x is, then I'm going to look at here. You can do this 20 minus 2x equals 0, or 12 plus 5x is going to equal 0. So on the left side here, I subtracted 20 from each side, then divided by 2 from each side, and I got x equals 10. Over here, I subtracted 12 on each side, divided by 5 on each side, and I get a negative 2.4. So to find out what my vertex value would be, how many reductions I need to make, we're going to do 10 minus 2.4. So we're going to take these two values, and we're going to try and find the average in the middle. So we're going to divide it by 2. So we have 7.6, that's just reducing this down, divided by 2, and we're at 3.8. So we're not going to make 3.8 $2 reductions. We need to test and see, is 3 better or is 4 better? So when we test this, we'll do it with R of 3 and R of 4. So all I did was I just plugged in 3 anytime I saw an x in this original equation. And so if you do that, type it in a calculator, get all your numbers, you're going to get R of 3 is going to equal $378. R of 4, when you do the exact same thing, is going to give you $384. So if we're looking at which one is the better option, this R of 4 is going to be the better option. You will make, it looks like $6 more than you would have before. So this one would be better. We'd want to reduce it 4 times. So what would our sale price be? So we'd take 20, and it's going to be minus 2 times 4. So it'd be 20 minus 8. So we get 12. $12 is how much we should sell each one of these for. So then see how much more the studio make by putting the sale price on as opposed to without. So we just do the total. They would have 12 that they sell per class. They charge $20. So they make a total of $240. So we take our new value, our 384, subtracted by our original, and we'll get $144 per classroom. So if you go to a school like St. George where there's a lot of classrooms, 144 is really going to add up quickly. So this is all I've got for lesson 23. Your homework assignments 1 and 2 will be fairly similar to these ones here. So when you get to them, if you get stuck, just come back and look at these. They should be able to step you through and should have a similar process. Number 3, that one's going to be a little bit more of a stretch, but it is following these processes that we've learned. So yeah, that's all I got for you for lesson 23.